everyone, welcome to the tutorial 6 of the mechanical vibrations. Today we are starting a new topic, which is the harmonically excited vibration of single degree of freedom systems. So this is the first video on this topic, and we're going to have a couple of videos on this topic because it's a very important topic in the vibrations. So let's just begin. Okay, so as you may know, a single degree of freedom system that we had before has no force or no sort of external excitation in the system. However, in many practical examples or in many problems, there is a force acting on the system. So let's imagine we have a single degree of freedom system as we had before. So we have a spring in the system, then we have a mass like M and K, and there is a damping in the system. So if there is no force, basically, so the system is a free vibration case that we had before. However, if there is a force in the system, basically, like acting on the system, like Ft, and it's a function of time, then the system is a forced vibration, or basically, if the force is a harmonic function, then we have harmonically excited vibration. So in this chapter and in this next couple of basically videos, we're focused on a harmonically excitation system, which means that the force is a cos or sine function. So basically it's F amplitude, then say for example you can use either sine or cos. We have cos omega t. So F is the amplitude of vibration and omega is the frequency of basically excitation or external excitation, which is very important for this case. So in other chapters we will see if there is like the force, but the force is not harmonic, then how we can basically find the response of the system. So remember, we are focusing on the systems that the force is a harmonic function, which is a cos or sine function. Okay, so as you may remember, basically the equation of motion for the system without the force was, we can say basically mx double dot plus cx dot plus kx equals to 0. But because we have a force in the system, then the equation would be Ft, right? And the differential equation is not a homogeneous differential equation. If you are not familiar with the homogeneous or non-homogeneous differential equations, you can basically check some of the videos in our channel about differential equation, and you can find more information about that. But anyway, so as we have a non-homogeneous differential equation, which means that the right hand side is not 0, the response of the system, or the total response of the system, is a combination of basically a homogeneous response and a private solution, or a homogeneous solution and a private solution. So in terms of differential equation, we can write it as xth, which h belongs to the homogeneous part, while we can also have xp, which is a private solution, and we call it xt, like the total solution. So this is the representation we use for basically the total solution of the system. In many notations, they call this part, the private solution, as the steady state, and you see today we have one example on that. And this is very important for the cases that we have a damping in the system, because after some time the homogeneous part will go away or will dissipate in the response, and we only have the steady state, and that's why we call it steady state. So it is important to know that. And how we can find the homogeneous part, basically we set F0. So for basically xh, we just set F0, or say Ft equals 0, and then we have a basically non-forced or just a free vibration case. We can find the response of the system as before, then we can find the private solution, and it has like its own formula, and then we combine the two solutions. And remember, when we have an initial condition in the system, we need to apply it to the total solution. I'll discuss that later on. So for today's examples, and as we are going to have a couple of videos on this topic, we suppose that the system has no damping. So we have an undamped cases for today, right? So remember that this is what we have, which means that basically there is no damping in the system, and this one is 0. So we have only a basically a single degree of freedom system, undamped, and we have a harmonic excitation on the system. And remember, sometimes the system is more complicated, so we need to find equivalent stiffness, equivalent damping, and equivalent basically mass, and then find the solution for the basically the equivalent equation of motion. Right? So let's begin with the first example. Okay, so here is the first case that we have today, and as you may remember, I said we have an undamped system, and today we are going to basically, if you go over the problem, we are going to find the total response of the system for a spring mass case. So it is just a simple 1 degree of freedom system, K and M, and we are going to find the total response. So we need xt, and both K and M are given, and we have a harmonic force which is given. So Ft is basically, this is Ft, and we know the function. The amplitude is 400 cos, and the frequency of excitation is 30 radian per second. And as you see, the unit is Newton, so everything is good. So we need to find the total response, and as you see, because we have the case that we need to find the total response, we need the initial conditions, and you will see why we need that today. Okay, so this is a simplified case. So the equation of motion is just, as you know, mx double dot plus kx equals to ft, right? And the response of the system is the summation of the homogeneous part and the private solution, right? And that's the basically the solution for the case that we have today. So first of all, we need to find the natural frequency of the system. For this simple case, we know omega n is equal to k over m, and we have both the values for k and m. It gives us 20 radian per second. So this is basically our natural frequency of the system. So for the system that we have an undamped case, and we need to find the total response of the system. So response would be in a form of, like I said, the summation of the homogeneous part and the private solution, which gives us like A basically cos omega n t plus B sine omega n t. And as you remember, when we have no force, this part like this resembles this response of the system. So this part is the homogeneous part, and then we have basically the non-homogeneous part, or the private, or the steady state, whatever we can call it. So let me just write it down as plus. This is a different term, which is basically C cos omega t, right? So for this part, which is x p, we know C. If just go over the textbooks, C is given as F naught over K minus M omega squared. So this is what we know from the textbooks. However, to find A and B, we need to apply initial conditions into the total response of the system, right? This is total response. So by applying, so using basically initial conditions into xt, then we can find basically A and B. So we can find A and B, right? So if we do so, and how we can do that, basically you have xt, you find the first derivative, and then which is basically the first derivative is the velocity. So we have the initial conditions for the displacement and for the velocity, then you can plug it into the displacement and velocity, and then find A and B, right? This is how we can solve a differential equation having the initial condition. So, but the easy thing is we have the formula for the total response of an undamped system. So xt is basically x naught minus f naught divided by k minus m omega squared. So as you see, this term also exists in the coefficient because we applied the initial conditions to the whole system, right? Or to the total, like the total response. So this is m omega squared cos omega nt plus x dot naught divided by omega n sine omega nt. So this is the homogeneous part plus what we have for c, which is basically f over k minus m omega squared times cos omega t. So as you see, the homogeneous part has a frequency of omega n, while the private solution or the private part has the frequency of omega, which is basically the frequency of the force, right? So by having the response of the system as this formula, we just need to plug in the initial conditions and the values for f naught, k, m, and omega, and then just simplify. So basically we have everything, and here f naught is 400, right? So let's just do that. So we can basically find the total response of the system. So x naught we know as 0.1 meter, and x dot naught for the initial velocity 0, so makes it even easier to calculate. So xt, if we plug in into the previous equation I showed you and then I simplify for that, we have 0.1 minus 400 divided by 400, yeah, or actually 4000, this is k, minus 10 times 900. As you remember, basically omega squared is 900. So then we have cos omega n t, or let me just use the value for omega n here. So then we have 20 t, we found omega n as 20, plus 10 over 20 sine 20 t, or actually we have to, I'm gonna use a different formula. I think I made a mistake here, so let me just rewrite it here. So this is the part for the homogeneous response, and then we have the part for the private solution, which is basically 400 divided by 4000 minus 10 times 900. 900 is actually omega squared cos and then omega, which is 30 t, right? So we can further simplify it and find the response of the system in a simplified version. So we have xt, if we simplify above equation, is 0.18, and then we have cos 20t minus 0.008 cos 30t. So for these initial conditions, this is the total response of the system, right? So we will be able to find the explicit expression for xt. So it has two parts with the natural frequency of the system and basically the frequency of the force, right? So this is what we're looking for, this problem here. So if you go back and then see, we have x naught 0.1 and x dot naught as 0, right? So this is what we applied here. Then I go to my solution, and this is the final solution. Okay, so something I just need to discuss with you before we basically continue to the next problem. So just keep in mind this equation for x, and then we can basically have more discussion on the response of the systems. Okay, so for this system, we basically found the total response of the system, right? As a combination of two basically cos functions. And one thing that I want to discuss today, so we found omega n as 20 radian per second, and we know that the omega the frequency of excitation is 30 radian per second, right? So let's define something called the frequency ratio, and it's normally written as R, which is equal to omega over omega. And you will see that a lot in the future. So for this case, it is 1.5, and there is no unit for that. Okay, so if instead of the time response of the system is a combination of sine and cos, so it's gonna be something like that. We don't care, right? It's just a combination of two harmonic functions, right? And then one thing that is very important to plot in the vibration analysis is basically the frequency ratio and the max amplitude. So if we have the total response, we manage to find the max amplitude at different and plot it with respect to R for the case that R is equal to 1. So imagine the case that omega is omega n and R is equal to 1. We will find the case that we have a resonance in the system. So this is the initial condition. And then, so for this case, the response goes to infinity. So why it's important? For this case, it is 1.5, which means that it is somewhere here for our case. So the amplitude is limited to, or the max amplitude is limited to a specific value, not necessarily equal to x naught. It's a different value, right? But we just want to discuss the case that there is excitation, but it is not going to infinity, or it's not a resonance case. But if you select the frequency of excitation in a way that omega is equal to omega n, then you're gonna get an infinite amplitude, like in theory basically, or the system will break down in practice. Then the amplitude goes to infinity. So we call it resonance, and you will see that in the future. Okay, so that's everything for this example, and we're going to continue on the next example. So this is actually the next example, which is our last case for today. So in this system, we are going to find the response of the system, but today, or for this case, we only focus on the steady state response. And as you see, no initial condition is given. So we are going to find the equation of motion and the steady state response of the system, and all these values are given. Why we need to find the equation of motion? First, because the system is not a simple mass spring case, and we need to simplify it, and we basically need to find equivalent stiffness, equivalent mass, and then use the solution for steady state response. So this is another type of problems that you will see, that you need to end up into a simplified differential equation with equivalent components. So as you see, for this case, we have theta as the degree of freedom. So we are basically looking for something like J equal theta double dot plus, and there is no basically damping in the system, K equal, and it's a torsional stiffness or spring constant, theta equals to, and again here because we're dealing with some moments, and then there will be like a m, and it is different from the mass. So let me just say we can use other equations like mt or m equal. It's not mass. Let me just use another basically variable or parameter for that. I'm gonna call it T torque equal times, and it is a harmonic. We can have sine omega t. So we are looking for something like this, or even you can call it F or whatever, and then we use the solution procedure we have for the steady state response. State response of a single degree of freedom system, and when there is no damping, we already know that the theta, or the private solution, is equal to we have like T EQ divided by basically K equal, right, minus M or J equal omega squared, right? So something like this. This is the amplitude times sine omega t. Why sine? Because sine is the term of harmonic force or for harmonic excitation we have. So if I quickly go back to the previous case, and then for the case that we have the response, see this is the private solution, or sorry, let me just show you again. Here we have the private solution, and this is here. So in this case, because we have a sort of rotation, instead of F naught, we have the amplitude of the equivalent moment, K is the equivalent stiffness, and M is J equal. So pretty much the same, right? So we're looking for the steady state, which is this part, right? So I hope you got the point. So let's go back to our own problem and see how we can basically find the response of the system. So once again, we are looking for the steady state or the private solution. Okay, so let's do that. To do this, first we need to use the method that we learned in the previous cases. So let's just give a sort of tiny virtual motion to the system. So this is the original position. So we give, and I'm gonna exaggerate on this, but so you can imagine it's a tiny theta. So what happens is we have at the spring K1, we have a force basically resisting against the rotation, which is basically equal to K1 delta 1, right? And this is delta 1. So at the other point, or on top, because it's going down, there is a force again resisting against the direction of motion, which is K2 delta 2, and you know that this is delta 2. And finally, we have the mass of M, we have the force Ft. So the force Ft is applied to the mass M. But interestingly, here we have also the mass for the rod, right? So the rod also has a mass. Okay, so let's see how we can derive the equation of motion for this case. So basically, first thing we need to know is delta 1 and delta 2. If we suppose that theta is small, we can assume that delta 1 is nearly equal to basically this gap, or this distance, sorry, A times theta, right? We had it before. It's actually A, for example, we can call it A sine theta, or basically A tan theta, but we can just use A theta here. Same thing for delta 2. We can suppose that it's equal to this distance B, and basically delta 2 is equal to B theta, right? Again, it is basically B tan theta or sine theta, whatever, but we know for small angles, theta is nearly equal to sine theta and tan theta, right? So these are the two assumptions we have. Now, how we can find the equation of motion? As usual, we use the Newton's law, the Newton's second law, sigma m over O, all the moments, is equal to basically J over O theta double dot. However, you see both the rod, or basically the bar, rigid bar, has a mass and there is a lambda mass in the system. So remember, for JO, basically JO or JEQ is the combination of the JO of rod plus JO of mass, right? So we need to find them one by one. Okay, so keep that in mind. So let's do it again and see quickly what we have. So we have basically one force here, K1 delta 1, one force there, K2 delta 2, and then we have this mass, this is theta. So if we write the equations and see how we can basically find the equivalent moment. So sigma, we had sigma MO equals to J equal, or JO theta double dot. Let me double check. Yeah, so that's here you can use JO or J equal for this case. So we go back to our solution, and then let's find the moments. So the moment resulting from K1 delta 1 is in the opposite direction of theta. So we have minus force times the arm of moment, which is A here with respect to the point O. So we have K1, and what is delta 1? It is A theta times A, right? A is the arm. Same thing for this force. We have minus K2 delta 2, which is B theta and times the distance here to there, which is b, right, times b. So that's not everything. We also have a force F, and as you see, the force Ft makes a moment in the positive direction of theta. You can remember why it's positive or negative, why we are using minus sign or positive sign from the dynamics. So we have plus Ft times the whole length, right? Because this is the arm of moment. L equals to, then we have J equal theta double dot. And what is J equal? J equal, we need to find it separately. So we have J equal times, or we don't need to use the brackets here. So I'm gonna erase these two. And then we have theta double dot, right? So the only thing we need to find is J equal. So for a rod, the Jo of rod, we can find it from the table or formula sheet. With respect to one end, if it is pinned with respect to one end, it's equal to 1/3 of ml squared. And for the lump mass, we know for any lump mass, the moment is the mass times the distance squared. This is the formula. So L is the distance and m is the mass. So this is actually the Jo. So let me just, instead of using rod here, I'm gonna use basically J equal. How we can find this? Basically, like I said, from the tables in the textbook, we can simply find it. So we have the equivalent in J or the moment. Now we can simplify this equation. So now we're going to simplify this equation and put everything in the left hand side except the external force and rearrange the equation. So if we basically simplify the previous equation, what we get is basically 1/3 of ml squared plus m, the capital M, L squared. This is J equal theta double dot plus K1A squared plus K2B squared theta equals to FL, which is F naught L sine omega t. So this mimics basically the equation we have for a simplified system. We have a J equal, right? This is J equal. We have a K equal, and we have this T or torque equal, whatever we can call it, or M equal we have. So we can basically use the formula we have. So theta, and we are looking for the private solution, is equal to like theta whatever sine omega t, same function as the force or the moment, and same basically frequency. We only need to find theta, and theta is basically from the formula we have. So I'm going to write it here. Theta is equal to, well, we have F naught L, the force amplitude, K equal minus J equal omega squared. And we have every single components of this equation. So if we plug in all these values, basically for F naught L, K equal, J equal, we can simply find. And remember, this is the capital theta, the amplitude. So I should write it again. So this is basically this theta, right? This is the theta we have, the amplitude of vibration for the steady state response. So if we plug in all the values we have, the amplitude or the capital theta, I'm gonna use a different color, like theta, would be equal to minus 8.572 times 10 to the power of minus 4 radian, right? It's a tiny amplitude, right? So this is actually the amplitude. So basically we will be able to find the steady state response of this system. So that's all the examples we have for today. In the future, we are going to work on the systems with the damping and how we can find the responses. I hope you enjoyed the video and stay tuned for the next videos.